Okay, you've made it to the end of Unit 9, and we're going to review all the basic integration formulas you've learned so far from the Calculus AB course. Now, there is a summary of all the integration formulas you are expected to know on page 211 of your book. And the list is quite overwhelming. Forget the seam, it is. But if you think about each of the formula as you use it, and if you work on memorizing these formulas, you should be actually okay for AP Test Day. Okay? Now, memorization is not enough by itself. Integration is really not as straightforward as differentiation. So, you need to do the following. Okay? Understand when to use them. Recognition of when or which formula to use. Using algebraic techniques to manipulate or substitution to put them into formulas that are nice. And most importantly, lots of practice. So to illustrate how complex this is, look at example number 1. Questions A, B, C, D. They all look very alike, yet they all have different integration formulas. If you look at part A, notice the denominator is 1 plus x squared. That should give you a hint as to what type of integration this is. We just did this recently in Unit 9. And if you said yes, this is the same thing as arctangent of x, you are correct. And if you look at part B, it's no longer 1 plus x squared in the denominator, but 1 plus x. In this case, because it's just x in the denominator and you're integrating that, I hope you remember that this is like a natural log of the absolute value of 1 plus x and then plus c. And that's what you get from part B. Now look at part C. There's a 1 plus x squared. You're like, oh, it must be arctangent. But wait, there's an x in the numerator. So hopefully in this case you recognize this must be u substitution, because the degree in the numerator is 1 less than the degree in the denominator. And then you get this du over 2. So in this case, sorry, 2x, my fault. Integration of x, and then dx becomes du over 2x all over u. Cancel them out. That's the integration of 1 over u with a half in front. And therefore you just get 1/2 ln of 1 plus x squared plus c. So once again, another natural log question. And if you look at part D, notice this is 1 plus x all squared. I'd suggest you rewrite that as 1 plus x to the power of negative 2 dx. And then you can just use the general power rule to help you out here. Add 1 to the exponent, divide by the new exponent, plus c. Look at this. 4 totally different answers for 4 very similar looking questions. Yikes. Now looking at example number 2, these are also similar too. Lots of ln x's and x's. But I hope you can think about u substitution to help you out for all of these. Because for part A, if you let u equals to natural log of x, du dx is just 1 over x. And so dx equals to x du. And therefore, if I were to now change this, dx is x du, x with a u, notice these just simplify to 1 over u du, and that's equal to ln of ln x plus c. I'd ask you to do something similar for part B. Once again, let u equals to ln x. I will just say dot dot dot, you get dx equals to x du again. In this particular example, u is the top, x is still on the bottom, and x du is now your dx. Goodbye, goodbye. So the integration of u du, this just becomes u squared over 2 plus c, and therefore we can replace the u with natural log of x all squared over 2 plus c. So once again, two lookalike functions, two very different solutions after doing the integration. So what other things might you need to do? Well, sometimes I'll ask you to multiply or expand things out before doing the integral. Sometimes we have to do term by term division, especially when you're dividing by a monomial, so that's just one term. Long division, of course, occurs when you have a degree of the numerator being greater or equal to the degree of the denominator. And sometimes this one, which is the most tricky, is splitting or separating the numerator into two separate fractions. So there are more complicated ones, and those will be discussed in our final lesson of the course in 9.7. But for now, let's go on to 9.6's page 2 questions. Alright, notice that examples 3, 4, 5, 6 are really illustrations of those four types that we had on the previous page. So, if you think about number 3, I would suggest that we all expand this out. And so if I were to change this and expand it out, we're squaring things, so e to the 2x squared just becomes e to the 4x. You have those two terms in the middle multiplied together, times by 2, right? Remember, a plus b squared. Remember that? A squared plus 2ab plus b squared. So this becomes 2 times 2 is 4, e to the 2x. And then 2 squared is just 4. So notice all I've done is expanded it out, and now I can integrate this term by term. The antiderivative of e to the 4x is just e to the 4x with a 1 over 4 in front. E to the 2x, of course, with the 1/2 in front. And the antiderivative of 4 is just 4x. We can simplify this and write this as 1/4 e to the 4x minus 2 e to the 2x plus 4x plus c. Done. Take a look at number 4. This is the one where there's a monomial in the numerator. So we can simplify this by just separating this into 3 terms, each divided by the denominator. I would still suggest us to simplify. X over root x is just root x, or x to the 1/2. The middle term just becomes minus 2, and our last term is actually x to the negative 1/2. So now I'll ask us to antidifferentiate. X to the 1/2, we're going to add 1 to it, divide by the new exponent, or multiply by 2/3, 2x, and then here x to the power of positive 1/2 divided by 1/2, which is the same thing as multiplying by 2. And don't forget your plus c. Now notice for number 5, we have the degree of the numerator equaling the degree of the denominator. So let us go ahead and do some long division this time. X squared goes into x squared how many times? You bet, 1 time. 1 times x squared plus x just gives us x squared plus x. We'll subtract to give you negative 2x minus 1. And that is my remainder. So this just becomes the integral of 1 plus negative 2x minus 1 all over x squared plus x dx. And we can simplify this a little bit more if you want by just taking out the negative, and that becomes 2x plus 1 over x squared plus x dx. And once again, you have to then solve. The first part is easy. This part is a little bit tricky. I'm going to think about using u substitution. I've done enough u substitution, I think, in the last little while that you should know how to do this. So actually, I'm going to leave it and go dot, 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 dot. And I'll just give you the final answer, and I want you to confirm that I am not lying to you. That's your job. Okay. All right. And then the last one here for number 6. case, I'd suggest us split up the numerator. So once again, it's like number 4, where you have one monomial in the denominator. You can rewrite this as integration of 3 over root 1 minus x squared minus the integration of, or dx. Or maybe what I'll do is this instead. Let me erase. Minus x over root 1 minus x squared, the whole thing with dx. And now I'll suggest us separating it. I'll take out the 3 from the first one. Do you know what that integral is? If you said arctangent, I'm very, very sorry. You are close. If you said arcsine, I'd say you are very, very correct. And then over here, I see x squared in the denominator and x, so hello, some u substitution again. Oh, I don't want to do u substitution again. Dot. And I'll tell you that this just finally becomes plus 1/2. Sorry, not 1/2. Plus, I believe, 1 minus x squared to the power of half plus c. And that would be your final answer. And of course, I want you to double check that for me. And by the way, once again, just a quick note, don't make this typical error. 1 over x squared plus 1, splitting that up into 1 over x squared, and also 1 over 1. Don't do that. You cannot split them up when it's in the denominator. You can only separate when it's a numerator. So in this particular case, when you get that, how do you integrate this problem? Now, if you said arctangent of x, I'd be very, very happy. Okay. So finally, for this section, can we just do these last 2 examples? And you will need to use u substitution. In this case, when I have sine and cosine, that's kind of nice because sine's derivative is cosine and cosine's derivative is negative sine. In this case, which one should I let equal to u? Because of that e to the power, I believe that u should be actually cosine of everything that's there, cos 2x. The derivative du dx is just negative sine 2x with an extra factor of 2. And you'll be thinking, oh no, an extra factor of 2, but that's okay, it's just a constant. So dx is just equal to du over negative 2 sine 2x. And now I think we're ready to do the antiderivative. I'll just write down sine 2x here. E to the u, and then dx becomes my du over negative 2 sine 2x. Perfect that the sine 2x is divided out, and you're left with just negative 1/2 that I can pull out in front. E to the u du, which is nice because the antiderivative of that is just e to the u. And let me just replace the u back in with cos 2x. Voila, we have our answer. And similarly for numero 8, number 8, maybe we need to do some u substitution here as well. In this case, I see tangent and secant, so that kind of helps me think, if I let u equals to tangent x, its derivative du dx is secant squared x. And that's good because that's what I see in the numerator. So now let's see what happens when I make my u substitutions. Secant squared x is still on the top, but now it's u squared plus 9, and dx now just becomes du over secant squared x. Perfect, because that simplifies to 1 over u squared plus 9 with the du. Hopefully you can see this is an arctangent question with a equals to 3, and I guess x equals to u. So x prime is just 1. That all works. You can use the formula if you want, which is 1 over a, so 1 over 3, arctangent of x, which in this case is u over 3 plus c. But I should replace back the u with what we started with, which was, oh yes, tangent x over 3 then plus c. That, my friends, is the correct answer. Okay, I'd make sure you do all these problems here, okay? 1 to 15 and beyond if there are more. Yeah, do them.